Hello everyone, my name is Tao Xiao, PhD student from Naro Institute of Science and Technology, Japan. Today, I would like to present my journal first paper, Characterizing and Mitigating Self-Automated Technical Debt in Build System. First, let's begin with what is technical debt and self-automated technical debt. Technical debt is a design or implementation construct that is expedient in short term, but sets up a technical context that can make a feature change more costly or impossible. Technical debt could be automated or noted as comments by developer to remind about the portion of the software that contain technical debt. These comments are called self-automated technical debt. The term was introduced by Porter and Shihab in 2014 as special case of technical debt. STD is widely studied in source code files for the aspects of frequency. STD exists in 31% of the source code files, and it can be classified into 5 main types based on the reasons of STD. For the importance of STD comments, STD changes lead to less feature defects than non-STD changes. 88% of the practitioner mention self-admitting the bad implication of the code through comments. This reflects the practical importance of addressing STD during development process. Current research mainly focus on STD in the source code file. However, there is no research looking at STD on the other software artifacts. Modern software development have a broader scope than solely producing source code. STD exists in various channels, which should also be considered to a global picture of technical debt. Next, I will explain why we choose the build system as one of the software artifacts to study STD. Build systems are responsible for automatically transfer the source code into deliverable. Build system combines the two into repeatable process. In 2011, McIntosh analyzed 10 large long-lived projects by mining version histories, and the study showed that build system maintenance is 27% overhead on the source code development. This finding brings one question. If build system maintenance is overhead than the source code file in terms of maintenance, does STD exist in build system such as Maven build system? Here are 2 STD comments that are extracted from Maven build system. As shown in those 2 examples, we can see location, reason, and the purpose of all STD occurrence could be different. Concerning location, upper one near the dependency tag, but the bottom one occur near profile tag. In terms of reason, upper one occur since the code is to download the dependency. However, the bottom one it occur because of issue in deployment. For purpose of developer left the ST comments in upper one, this comment was left by developer to provide workaround, while in the bottom one, this comment was left by developer to warn other developers. Motivated by those examples and observation, we conduct an empirical study to analyze the characteristics of the STD comments. The goal of this work is to establish an understanding of STD in build specification file and help developer be aware and manage those STD. Our studied projects are targeting to the Maven project, the most popular package manager, and automatically build system for Java. We divide the research question into three parts. RQ1, what are the characteristics of STD in the build system? Even though STD comments are widely investigated in the source code file, it's still unclear what kind of STD comments exist in build file. It will provide a foundation for understanding the scope of STD problem in build file. Since RQ1 is not scale enough for large-scale analysis of STD category in build file, RQ2 can automatically classify accurately identify characteristics of STD in build system, can promote large-scale analysis of STD category in build file. RQ3, to what extent can STD be removed in build system? The manner of handling STD is unknown. We investigated a subset of STD removal by submitting progress and issue reports. Answer this research question can address the necessity of proposing automatic tool to identify STD comments for researchers. We manually read 500 STD sample, identify 9 STD locations, STD tend to occur in the plugin configuration and external dependency configuration code. From 500 STD comments, we identify 60 sub-reasons, merge them to 9 reasons that why STD occur in Maven build system. The most frequent reasons include the limitation in tools and library and complexity of dependency management. For why STD introduced by developer, we identify 6 purposes in Maven build system, documenting issue to be fixed later and explaining the rationale for workaround are occurring the most frequently. We further visualize the relationship between location and reason, and the location and the purpose by using 2 parallel sets. From this diagram, we can say location category tend to be more prone to STD reasons. In summary, we identify 9 STD location, 9 reasons, 6 purpose in Maven. Location category tend to be more prone to STD causes. In RQ2, we compare both traditional and state-of-art machine learning technique to classify STD reasons and purpose from those 500 STD samples. We find outscaling-based classifier achieve the highest value over the set of baseline classifier. The result shows that the feasibility of training automatic classifier to identify STD characteristics. From those 500 STD comments, we identify a subset of STD which refer to the STD comments that contain result bug report. We create the issue report and pull request to address those comments. After proposing those repayments, we receive feedback from the developers. Those response of STD repayments suggest the developer are receptive and reactive to STD in the build system. We also send a survey that contain 10 STD cases to incorporate developer perception on instance of technical debt, understand the real-world experience with similar instance of technical debt, and evaluate the stability of proposed reason and purpose categories. We invited 1,670 developers who have had at least 10 contributions in our studied project. We received 20 responses. Half of the respondents have more than 10-year experience on Maven EDID. The table shows that in each of the 10 prepared cases, more than 50% of developers agree with the instance of a technical debt. In the survey question, we also ask developers whether they have experience with similar example of technical debt. The survey results show that for each of the 10 cases, at least 58% of the developers have had a personal experience with similar example of technical debt. For evaluation of reason and purpose category, most of our developers are consistent with our labels. We also have some comments from developer. The first comment is elaborate on how best to deal with cases of inadequate licensing information on Maven. A respondent explained that some debt are inherited because of decision-making by upstream dependency. One survey response pointed out STD causes by external library limitation produce maintenance nightmare. For the takeaway message, we recommend the partner to check STD that contain result bug report. We identify 60 instances of STD comments that contain result bug report from RQ3. Those stale STD comments could create confusion for anyone inspecting the code. We recommend the researcher to further study the workaround for STD. During coding process, we observe one STD workaround can be used across several repositories. Thus, it is valuable to study workaround of STD. We recommend the tool builder to build a tool support for managing STD in build system. It could be practical useful to have tools or system to help a partner manage the STD traceability automatically. To conclude, our work is first to characterize and mitigate STD in the Maven build system and explore the feasibility of training automatically classified to identify STD characteristics. In the future work, we plan to expand the coded corpus of STD comments to other build systems. and further study on the duplicate workaround of STD, and build a tool support for track and manage STD backlogs. That's all for my presentation. Thank you for your listening.